continue our discussion of symmetry with the rotation operator. First, we'll introduce the rotation operator, then we'll talk about continuous rotation symmetry, and finally we'll look at different kinds of operators and how they react under rotation and parity symmetries. So, the operator R sub z of alpha rotates the function an angle alpha about the z-axis. That is, R sub z of alpha applied to psi of r, theta, and phi is equal to psi prime of r, theta, and phi. And it's also equal to psi of r, theta, and phi minus alpha. So just like the translation operator, we can now determine the generator of rotations by starting with the Taylor series, and we're going to leave out the r and theta because they play no part in this. So R sub z of alpha applied to psi of phi is equal to psi of phi minus a, according to our to how the rotation operator works. But we can expand that in a Taylor series as a sum from n equals 0 to infinity of 1 over n factorial phi minus alpha minus phi all to the nth power, and then the nth derivative of psi of phi minus alpha with respect to phi minus alpha. And all that evaluated at phi minus alpha is equal to phi. Well, we can take this term here in blue and the term in green and simplify them. And so we get sum of n equals 0 to infinity, 1 over n factorial minus alpha to the nth power, because that's all that left when you add together these terms. And then over here you have a replacement of variables of phi minus alpha. We just replace it with phi because we're evaluating it with phi anyway. So then you have the nth derivative of psi of phi with respect to phi, all evaluated at phi. Well, because it's evaluated at phi, we can simplify this a little bit further and write this as a sum from n equals 0 to infinity of 1 over n factorial minus alpha to the nth power, the nth derivative with respect to phi of psi of phi. Clearly, we can now do the same thing we did with translation, that is, multiply times I over h bar and h bar over I, which is just 1, and then isolate this term here, which is h bar over I d by d phi. Well, that's simply the operator L sub z. So the final sum becomes sum of n equals 0 to infinity, 1 over n factorial, minus I alpha over h bar operator L sub z, all to the nth power applied to psi of phi. But this is simply a sum which gives you an exponential function. And so this is equal to e to the minus I alpha L sub z over h bar applied to psi of phi. But that means that comparing this term and this term up here, that R sub z of alpha is equal to e to the minus I alpha L sub z over h bar. A consequence of the Hamiltonian commuting with the translation operator was the conservation of momentum. Similarly, because the Hamiltonian will also commute with the rotation operator, this will lead to a conservation of angular momentum. If you have a central potential, that is, V of r is equal to V of minus r, then the Hamiltonian is rotationally invariant, the Hamiltonian being p squared over 2m plus V of r. And that means that it commutes with the rotation of any angle in any direction. So if you take a direction n, a unit vector n in any direction, and you apply a rotation around that axis, that operator will commute with h. So for an infinitesimal rotation, this also must hold. And an infinitesimal rotation delta means that the operator, which had a form e to the I minus I alpha L sub z over h bar, can be expanded in only the first two terms, and we can ignore terms in higher order and delta. So we keep only terms to first order in delta, and we get that R sub n of delta is equal to 1 minus I delta over h bar n dot L. So you pick out the angular momentum component along the axis of rotation. So the Hamiltonian, therefore, must also commute with L. That is, H and L commutator is equal to 0. Because of Ehrenfest's theorem, we now have that d by dt of the expectation value of L is equal to I over h bar expectation value of the commutator of h and L, which by definition is 0. And so the time derivative of the angular momentum expectation value is also 0, which means that you have conservation of angular momentum. And so consecration of angular momentum is a consequence of rotational invariance. Since h, the Hamiltonian, commutes with all three components of L, it must also commute with L squared. It's therefore possible to choose a set of three compatible observables which mutually commute. And this means that you can choose h and L squared, which commute, h and L sub z, which commute, and L sub z and L squared, which also commute. So any wave functions that we have, or eigenfunctions that we have, can be eigenfunctions of all three of these simultaneously. These are the hydrogenic-like states. The h applied to psi nlm is equal to E sub n psi of nlm. L sub z applied to psi nlm is equal to m h bar psi of nlm, which m h bar being the expectation value, or the eigenvalue. And L squared applied to psi of nlm is just L times L plus 1 times h bar squared psi of nlm, as we've seen before. Therefore, the three quantum numbers nlm will uniquely specify the bound state of the rotationally invariant Hamiltonian in 3 dimensions. This isn't restricted to the Hamiltonians we've studied already, but holds generally for any central potential. Now finally, it's useful to talk about classification of operators under symmetry operations. So depending on how an operator transforms under rotation and inversion, or parity, it can be classified as a vector or scalar operator and a true or pseudo quantity. So in this table, we talk about the operator, the type of vector it is, how it commutes under parity, or how it transforms under parity, and how it transforms under rotation, and then some examples of different operators. The first one is a true vector. A true vector is also called a polar vector. It is an anti-commutator of parity with any one of its components. And the anti-commutator, as you can see down here, is that A plus B is equal to B plus A. So this is the anti-commutator. It also behaves under rotation as the commutator of L sub I, which is the angular momentum, so that's rotation generator, and V sub j is equal to I h bar E I j k, and then V of k. And these operators are R and P are good examples of these operators. When you apply parity, they reverse direction. A pseudo-vector is what is called an axial vector, and that has a that commutes with parity. Any component of this vector V will commute with parity, and it also has a commutator with the angular momentum component I and V of j sub j of I h bar E epsilon I j k V of k. So very similar here. The only difference between the polar and the axial vectors is how they behave under parity. An example of these, or two examples of these, are the angular momentum vector and the magnetic field B. A true scalar doesn't have a vector type because it's not a vector, but it commutes with parity, and it commutes with any component of angular momentum. An example of this would be r squared, which is r dot r. Now, since r is a polar vector, that means that the dot product, or the scalar product of two polar vectors, gives you a true scalar. A pseudoscalar anti-commutes with parity. So when you apply parity, it inverts. And it commutes with rotation, any of the rotation components. And an example of this would be the flux, the magnetic flux phi b. Now, phi b is simply the magnetic field dotted into a surface vector, surface area vector. And so this is a polar vector, but b, as we can see up here, is an axial vector. So the scalar product of an axial with a polar vector is a pseudoscalar. In all these, you could replace L sub I with either J sub I, the total angular momentum, or S sub I for spin.